So we're going to look at high availability, and what we're looking at here is the various features and technologies that we have available to us to help us ensure that our services stay up and functioning. And there's quite a few different things we're going to look at here to help us maintain connectivity, maintain our services up, help us keep systems up and running. So we're going to look at characteristics of high availability networks, list and describe some of the features, high availability features, and look at configuring and monitoring some of these features. So here's a few we're going to look at. We're going to do an overview. We're going to look at a thing called graceful restart, which has to do with how routers manage routing protocols while the router is doing a restart, or if the router has to do a restart. Then look at a thing called graceful routing engine switchover, which is a feature available to us for routers that have got dual routing engines, and some of the higher end routers do. I mean, the thing to think about here is that if you're running an internet service provider, you can't just say, oh guys, we're just going to shut our router down for maintenance, or we're going to shut it down so we can upgrade the software, or whatever it is. You've got to keep this thing running 24/7. So there's some mechanisms, certainly in the higher end routers, that mean that we can do upgrades, we can do maintenance without ever having to take our routers down. A thing called non-stop active routing, we'll take a look at that. We'll look at a thing called BDF, look at a thing called VRRP, and another thing called unified ISSU. So high availability is the ability to ensure a high degree of operational continuity to a resource for a user community. So measured over a specific period of time. So really another term that is used to measure that is uptime. What is our uptime? As opposed to over a certain period of time, what percentage of time have our services been up over that time? So high availability networks include provisions that allow for the maximum amount of uptime and accessibility. Some key considerations is the base functionality of a network's hardware, software, protocols, and overall operations protected. And when a failure occurs, how will the overall system or network react? And what level of recovery can be expected? So we're looking at increasing uptime, decreasing downtime. So we're going to look at some features that the Juniper operating system supports to help us achieve high availability. Some of these features complement other features, whereas in some cases, some features might be mutually exclusive. Okay, so we're going to look at graceful restart, graceful routing engine switchover, non-stop routing, bidirectional forwarding detection, virtual router redundancy protocol, and unified in-service software upgrades. Graceful restart. Look at this scenario here. What would happen if R1's routing process restarted? So here we're running OSPF. We're OSPF area 0. So if R1 were to go down and do a restart, this routing process had to do a restart, what would happen? Well, the first thing that happens is that the adjacencies with the other routers would be dropped. So these other routers, R4, R5, R2, would recognize that they had lost their neighbor relationships, that the other router, R1, was dead, okay? It had died. So what would happen then is they would then have to update their link states. They would have to then send link state advertisements to all the other routers. All the other routers in the whole topology will then have to recalculate their routes based on the new topology that they then have to converge, and then they can start routing traffic again. A major disruption. Then what happens when it restarts? Well, then the adjacencies are reformed. They realize, oh, we've now got that neighbor relationship again. They then have to re-advertise link state advertisements again with all the updates. All the routers have to recalculate the whole topology and recalculate all their routes all over again and then converge. So big disruption if that happens on the network. And of course, routing is disrupted while all that's going on. Okay, so graceful restart allows a router undergoing a restart event to inform its neighbors and request a grace period during which it can recover from that restart event. So forwarding through the existing path can continue during the restart. Okay, so here's a question. How can R1 keep forwarding traffic while its routing engine is restarting? How can that happen? How can R4, R5, R2 keep forwarding traffic to R1 and R1 keep forwarding that traffic while its routing engine is restarting? How can that happen? Okay, you might have to cast your mind back a few weeks to when we first introduced Juniper technology and where we described this concept of control plane and forwarding plane and how they were two separate planes and how they were kind of separated. So what went on in the control plane didn't necessarily upset what was going on in the forwarding plane. So in other words, we can have our control, we can have our routing engine, routing process restarting in the control plane, and our forwarding plane still happily forwards traffic based on the information that is in the forwarding tables without affecting anything else. Okay, so traffic is arriving on the links. The links are actually up. We haven't dropped our links, we're just restarting our routing engine. Okay, so we're restarting our routing process. So traffic is happily arriving on the links and being forwarded through the forwarding plane while our routing engine over in our control plane is doing a restart. Okay, so even though we're not sending hello packets, okay, to our other neighbors because our routing engine is down, it's going through a restart, we're not sending our OSPF hello packets. We can still forward traffic through our forwarding plane. Okay, so forwarding can still continue quite happily. And so what happens is with the graceful restart, R1 notifies its neighbors, and this is something which is part of the OSPF protocol. It notifies its neighbors and said, hey, don't expect to see me for a while. I'll be out of here for a bit. And then it vanishes. Now the default is 30 seconds on a hello packet. Actually, that's the dead time. Every 10 seconds you get one, it sends, but the dead time is 30. So what if it took a couple of minutes, all right, to do the restart? Fine. As long as we're using graceful restart, we're okay. Okay, so there's a few standards-based protocols that support it. OSPF is, ISIS does, BGP, RIP, RSVP, LDP, MSDP, and PIM are protocols that support graceful restart. So we've got restarting routers, which is the one that's restarting, and helper routers are the other routers around it, must have graceful restart enabled and be able to support non-stop forwarding. So here we have a little diagram, our routing engine, and there's our packet forwarding engine, okay, separate. So our interfaces are up, our packets are still going in, they're still getting happily forwarded through our packet forwarding engine, and our routing engine is going through its restart, no problem. Okay. GA help mode is enabled by default. You have to actually disable it if you don't want it to be there. So it's enabled by default. You have to disable it. Under BGP, you enable graceful restart under the BGP protocol. Or you can disable it depending on your requirements. So GR restarting router mode is not enabled by default. So the helper mode is, the restarting mode is not, and this is something you do have to go and enable under the edit routing options protocol. Here it is, enabled under the edit protocol options, edit protocol BGP options as well. So we have enabled that. We can monitor it, verification, so show BGP neighbor peer address, and we've got the graceful restart appearing there. For OSPF, we can enable trace options with a graceful restart flag, and then we can see that in our trace options. Okay, so that's graceful restart. Had a look at that, what it does, the fact that we have to go and enable the restarting router, but the helper is enabled by default. Graceful routing engine switchover is something that we can use where we have multiple routing engines. Allows Junos device redundant REs to continue forwarding packets even if one routing engine fails. And so with graceful routing engine switch or without it, two scenarios here. Without it, the PFE restarts and all hardware and interfaces are discovered by the new master routing engine. The new master routing engine restarts the routing protocol, and all adjacencies are aware of the physical interface alarms and routing changes. With graceful routing engine switchover, the packet forwarding engine is not restarted and interface kernel information is preserved, so the switchover is faster. The new master routing engine restarts the routing protocol and all adjacencies are aware of the routing change. So essentially you have two routing engines, you put graceful routing engine switchover in place, and if one of them fails, the other one goes live and all is good. Summary of the operations. Once graceful routing engine switchover is configured and the REs are synchronized, keeper lives are exchanged. If the backup routing engine does not receive a keeper live from the master, the routing engine, typically after 2 seconds, determines the master routing engine has failed and takes over the mastership. The packet forwarding engine seamlessly disconnects from the old master routing engine, typically RE0, and reconnects to the new, typically RE1, and that the packet forwarding engine remains operational. And the new master routing engine and packet forwarding engine synchronized, after which the new master routing engine sends a state update messages to the PFE as needed. This is how we enable that. Some of the edit chassis hierarchy, and we go and set redundancy graceful switchover. It's actually the purpose of it is a failover mechanism. So you only ever have one being active at one routing engine active at a time. Yeah, so it is a failover mechanism. So we can verify it's enabled using the show system switchover command, and we'll see exactly what's happening, that the switchover is on, database is ready, etc., etc. Okay, so that was graceful routing engine switchover enabled under the chassis hierarchy for routers with multiple routing engines. Okay, non-stop active routing allows a mastership change to occur without alerting peer nodes of that change. So it uses graceful routing engine switchover infrastructure that must be enabled, and it preserves the routing information and protocol sessions. So little note here that NSR and GR mode are mutually exclusive. So you use one or the other. So basically the rule is, if you've got multiple routing engines or dual routing engines, you're going to use NSR in conjunction with graceful routing engine switchover. If you've only got one routing engine, then you're going to use your graceful routing engine restart. That's basically what you're going to do. Okay, so enable NSR under edit routing options hierarchy. You must also enable graceful routing engine switchover under the edit chassis, and essentially we can verify that is operational there. So essentially, similar thing, one of our running engines dies, the NSR immediately takes charge and makes sure that our neighboring routers are never affected by that change. Okay, it's never affected. Everything keeps going as usual. This is an interesting one. BFD, it's used in a lot of scenarios. Bidirectional forwarding detection. It's used to detect network failures quickly. So all modern protocols such as OSPF and BGP include some mechanism to detect failures. The problem is it's fairly slow. So OSPF timers can cause a router to take up to 40 seconds before it declares a link is down. 40 seconds is a long time to be forwarding traffic towards a dead link or out of a dead link. Okay, so that's 40 seconds of dropped packets. So, yeah, so what we're saying is, yeah. So, yeah, so what we're saying is we've got a link. A link has gone down here, so we lost connectivity to router 1, and yet we're still sending packets at that interface for 40 seconds before we've said, hang on, I don't have any connectivity to router 1. So router 1 might have died, or the link may have dropped. Either way, we have the same problem. So a little note here says you can reduce the timers. You can reduce the timers down, but the issue is you then end up sending hello packets instead of every 10 seconds. You can send them every 1 second, but then you're just sending hello packets like crazy, right, across your network. So you're consuming resources and consuming bandwidth with these hello packets. So the best solution is not to go around tampering with the routing protocols themselves, because then you have to go and configure every routing protocol that you are running to detect failures faster. There is a better solution, and that is to use bidirectional forwarding detection, which can run across all your routing protocols, and it's extremely fast. So a neighbor failure is detected when a router stops receiving hellos after a specified interval. So relieves the supported protocol by providing fast failure detection. Protocol timers can be left at the default values, or even increased to reduce processing overheads. This is the protocol timers in the routing protocols. Provides a single common method of managing protocol timers rather than modifying relevant timers for each protocol, each and every protocol actually running on the network. All the protocols that are supported: OSPF, ISIS, RIP, BGP, RSVP, PIM, and static routes. This is kind of really useful when if you're running VPNs and stuff like that as well. Just if your VPN is down, particularly if you've got multiple links, to a site, and you want to very quickly respond to a link failure, this is a really useful mechanism. Okay, so configuration hierarchy at which BDF is enabled varies between the protocols. So under OSPF, we are here under the area interface hierarchy. BFD liveness detection, minimum interval 300. So these are the minimum requirements. Enables minimum transmit and receive interval for BFD hellos. Transmit and receive intervals can be set separately and can use different values. So here we have 300 milliseconds as the time, 300 milliseconds, as opposed to your standard hello timer of 10 with a dead interval of 30 seconds. Okay, 300 milliseconds is about, what, 1/3 of a second, as opposed to 30 seconds. Okay, so we're talking 1/3 of a second as opposed to 30 seconds. Well, a hello packet maybe every 10 seconds. These are going well, about three a second minimum interval. Okay, so this is the show BDF sessions to view the session details, and we can take a look at a lot of information there. So here we have our sessions down there. We've got detect time. We can set up our detect time here. So in this case, the multiplier is 3, which is the default. So we're sending every 300 milliseconds, and if we don't get a response, or we don't get one for 900 milliseconds, we're going to say the link is down. Okay, in this case, we're sending it every 400, and if we don't get it within 1200 milliseconds, we're going to say that the link is down. Okay, so that is very fast timing. I mean, 900 milliseconds, well, it's 1,000 milliseconds in a second. Okay, so that's basically 0.9 of a second. That's 0.3 of a second with the intervals, and 0.9 of a second before we say, hey, the link's down. So very fast response. Okay, it declares the link is down, informs the protocol, hey, the link's down, and the protocol automatically says, right, I've lost my link. Okay, so very, very quick. We can adjust the multipliers, and you can adjust the time as well. So very nice feature to very quickly detect a down link. Okay, we have this. Let's look at this scenario here. What if R1, which is currently functioning as the gateway for 172.25.100.1/24 subnet, failed, or one of its 2 directly connected links became unusable? We have an end-to-end communications fail in that particular scenario. So here's a scenario where we have VRRP, which allows us to have multiple gateways on our network. One is the master, one is the slave. So it's a failover mechanism, means of incorporating redundancy and increasing network availability. So they communicate through a common switch to determine the master VRRP router and to detect failures. So what we're saying is here, what if our gateways failed? We will lose connectivity, and this is just a way. In fact, I wouldn't call it a gateway. What if our edge router failed? Gateway is a bad term. What if our edge router failed? And we will lose connectivity to the internet. So this is a way of overcoming that particular limitation. I would just say in relation to that this solution is not really a solution for most enterprises. And the reason for that is because the device that connects your enterprise to the internet is not simply a router. It is in most cases a gateway which incorporates a stateful firewall. So what we've got in there is a whole bunch of security policies which control access between the internet and different parts of your network, and quite often access between one part of your network and another part of your network internally is controlled by your gateway device. So it's not just a router. It's not like, oh, this one's dead, let's use the other one. It's not that at all. Okay, so in most cases, in most enterprises, this is not a solution for your device, for a failure of your device that connects your enterprise to the internet. Okay, this is not a solution. Yeah, so just say that's an SRX, okay, configured as a security gateway with security policies, with VPNs, with everything else going on. All right, this VRRP protocol is not a solution for that. Okay, there is a solution for that, and it's called clustering, where you can take your 2 SRXs, incorporate clustering so that they are operating in a failover situation with a master and a slave, but they are sharing all that routing protocol information, all of those sessions, it's all shared between them. So if one fails, the other one is good to go. Bang, just takes over right away and implement, and all your security policies and everything are maintained and intact. So this is just, oh, we have a router, it's a gateway, and it's connecting us to the internet. This is a protocol, which is an open standard protocol, which is designed for that scenario. I will say that most enterprises need much more than this, and clustering is really the solution for that. We will cover clustering next term when we do our security subject, get into clustering. Okay, but let's look at this scenario here. Our virtual router redundancy protocol, VRRP. Here we go. So we have a VRRP router. Any router participating in VRRP, including the master and all backup routers. A master router performing packet forwarding and responding to ARP requests. Why are ARP requests important there as far as this goes? What are ARP requests got to do with all of this, by the way? ARP requests. What's important about the fact that the router responds to ARP requests? Why is that? Make sure? Not really. It is the response of the ARP request that determines which router the packets are forwarded to. Remember, you've got a default gateway, okay? So what happens is, when you are sending packets to a network which is not the same network as which the device is attached to, it says, okay, that packet is going to another network, it sends it to its default gateway. So it has an IP address of the default gateway, okay? What it has to do, it has to encapsulate that particular packet into a frame, so it's an Ethernet frame, and it has to put a MAC address on that frame. And the MAC address is the MAC address of the default gateway. But what happens if I've got two default gateways? Which MAC address goes on the frame? That's the thing. We actually have to send it to a physical address, okay? So we actually do, the master router will respond to the ARP request. Okay, the backup router is available to assume the role of the master router upon failure. So the actual traffic goes to the master router. Virtual router is an entity that functions as a default router on the LAN, consists of virtual router ID, IP addresses, used as a gateway known as the VIP address, virtual router IP address. This is an open standard protocol, by the way. Okay, so it uses a multicast address, 224.00.18, confined to a local network, TTL equals 255, uses a set interval every second by default, requires that speakers be configured with the common settings, for example, virtual router ID and authentication parameters, use a virtual router MAC address for LAN communications. And the master VRRP router is determined by a priority value. Higher is preferred, so the default value is 100. If we set it if we want a particular router to always become the master, we set it to 255. And preemption behavior is optional. So in other words, we can say, what does preemption mean? Preemption means if I come and set the other router to a higher priority, then it will switch over and become the master. If we don't have preemption enabled, then it will not switch over by simply configuring a higher priority. Of course, it will switch over if the other router fails. States we've got initialized, where the router negotiates a VRRP roles through startup events, so no forwarding can perform what that is going on. Master assumes the traffic, a router assumes traffic forwarding responsibility for the LAN and responds to ARP requests. And as I pointed out, the reason that that is important is because the MAC address that goes onto the frame is ultimately going to determine where that packet, where that frame arrives. So which actual router is going to end up forwarding the traffic. Backup router monitors the VRRP router and is ready to assume the full responsibilities if failure occurs. And then we have a transition in which the router switches between master and backup states. So no forwarding can be performed while in this state. And here's our configuration here as well. So we've got our interfaces. We set up a group. We've got an address there. So this is R1. We've got R2. These are two routers. You can see we've got different priorities set on those two routers. They're both part of the same group. They both have the same virtual address, but they have different priorities. So which one's going to assume the master out of those two? Was it the higher priority or the lower priority that wins? Actually, it's the higher. In this case, it's the higher priority that wins. So in this case, R1 would actually become the master because it's got a priority of 200 and the other's got a priority of 100. Okay, so that would actually become master. A few different options we can configure on this protocol. We can track, monitor the state of the specified interface, typically a WAN interface, or route and reduces the designated priority value for the VRRP group if the tracked interface route is no longer available. So what that means is if we lose our upstream connectivity to the internet, then R1 will drop its priority, and what we would assume would happen then is then there would be a preemptive failover and R2 would then become the master. We can accept data, allows the master router to respond to ICMP requests sent to the VIP address. By default, the master router does not respond, so we can change that default behavior. Set up an authentication type where we authenticate the VRRP messages between the routers. The type and key must match, so we can actually authenticate those messages by setting up a type and a key, and no disables preemption to avoid unwanted mastership changes. So preemption is disabled by default, which means the router with the highest priority always assumes the master role. So of course, if you're using the track feature, you'd want to leave preemption on so that if in fact you did lose your upstream link, the other router would take over and you'd have a preemptive failover. And this is how we monitor the operations. So we can look at a bunch of different commands there. Show VRRP summary. We can see R1 is the master, and we can see also that R2 is the backup in that particular instance. Okay, so that was VRRP there. And the final thing we want to cover for today is unified ISSU, which really just allows us to upgrade the software on our router. In-service software update is what ISSU stands for. In-service software update enables you to upgrade between two different Junos OS releases with no disruption to the control plane, eliminates network downtime during the software image upgrade, and reduces operating costs by delivering higher service levels, sounds like the marketing department got involved here, and allows fast implementation of new features. So we have a few things enabled here. We have to have non-stop active routing enabled, which means we have to have our graceful routing engine switchover also enabled. So both of those things have to be enabled and working for us to use ISSU. This is, of course, feature is only available where we do in fact have multiple routing engines. Okay, so to perform a unified ISSU, complete the following: enable graceful routing engine switchover and non-stop routing, verify that the routing engines and protocols are synchronized, verify that the master and backup engines are running the same software version, download the new package from the Juniper Network Support website, and then copy the package to the router. Issue the request system software in service upgrade command on the master routing engine. Let me just stop that noise. Sorry about that. On the master routing engine. If the procedure stops progressing, you can open a new session on the master routing engine and request the system software abort in-service upgrade command and check the router session to verify that the upgrade has been aborted. So it's sort of similar to the request system software add command that we use when we're just upgrading a software normally, except we're using the request system software in-service upgrade command. So a very similar process. Okay, so in this chapter, we describe characteristics of high availability networks listed and describe some high availability features, configured and monitor some of those features. Here's some review questions. Describe the basic operations of GR. So what is that? GR stands for Graceful Routing Engine Restart. Okay, so you would use it when you only had the one routing engine. Okay, don't have dual, you only got the one. And how does it help us? If the routing engine restarts, then what happens? There's two major benefits to it. One is the forwarding plane keeps working, so we can keep forwarding packets happily through the router. And the other benefit is that the other routers that are attached to it, the other OSPF routers, don't think, uh-oh, my router is dead because I'm not getting any hellos coming back. And if you go past a 30-second dead interval, you say, okay, I've lost my router, and therefore we have to reconfigure the whole topology. So it stops all of that from happening. Okay, what is the key benefit to using Graceful Routing Engine switch over? It's kind of similar, really, in that if one routing engine fails, the other one takes over and we don't lose connectivity. We want to enable our non-stop routing functionality in that case so that we have an instant switch over and we don't lose any of our state, any of our protocol state. Benefits of using BDF, bidirectional forwarding detection. What's the benefits of that? It's fast. Yeah, the benefit of that is it's fast and it works across all the protocols. Purpose of virtual router. What's the purpose of virtual router in the virtual router redundancy protocol? What is the purpose of the virtual router? It has an IP address which is used as the default gateway on our network. Okay, so that becomes the default gateway address. Okay, so it assumes an address, another address, which is not the address of either of the physical routers. It assumes another address, which then becomes the default gateway address. All traffic is sent to the default gateway address, but it's actually the master router that responds to ARP requests, whichever router it happens to be. The actual physical router responds to ARP requests. And you have a lab on that to do as well. Alrighty, well, we're tracking pretty well. How's that? Any questions for that before we wrap up for the day? Okay. Well, that concludes our lectures for today, and we'll get into some more interesting